So in this video, I will talk about the mesh shading as a cloud. So we have a mesh and we are going to shade it as cloud, and we are not going to use Raymarching, but we could achieve the effect like the self-shadowing, the volumetric rendering. And the method is given in this GDC talk 2019 by the team of Sea of Thieves. It's a very smart method that what we are doing is we are baking the occlusion information into the vertex. So each of this model is being specifically, we save some spatial data into their UV2, UV3 in Houdini, and then we will design shader. So basically, yeah, just watch this talk first. It's very clear, and we can implement it inside Houdini and Unity and Houdini. But I would still like to go through the idea behind the rendering function. So this is the real-time rendering 4th edition about the volume rendering. And we know that this is the formula for rendering volume or something that has a medium. That is to say, we have a cloud here, and we have a light source here, and our camera is here, and this is an opaque object, and the Li means the radiance into the camera from the direction, the view direction. So this is the radiance to the camera is equal to the transmittance to the light coming out of the position and the view direction. So the transmittance by definition, where is the transmittance? The transmittance by definition represents the ratio of light that is able to get through a medium over a certain distance. So we have a Lambert law to calculate the transmittance. So in this example, if we wanted to calculate the light into the camera, the first term we have to multiply the light coming out of the opaque object and by the transmittance from the C to P, because we are inside the cloud. So we have to calculate this transmittance. And another term, this is much more important, is that when the light is coming into the cloud, it will scatter. And so this is the light scattering term to the camera. So the amount of light into the camera, and we also have to times the transmittance again. And of course, we are going to integrate for each of the point. In theory, we are going to use Raymarching and multiply by a coefficient called the extinct coefficient. And so how do we going to calculate this light scattering term? Of course, the light scattering term, this is the light scattering term. So this is how we calculate the light scattering term. It's equal to, we are going to calculate the light scattering. This is the sun, and it comes light coming into the cloud, and it will scatter. And we are only interested in the at this position, the light scattering along v direction to our eye. So it's equal to we run through a sigma to run through all the lights. Let's just assume we have one light. And we have three terms: the phase function, the visibility term, and this is just like the attenuation, the light, and we have a distance from x to p. Like point light, we will have attenuation, but for direction light, we don't have it. So this is just the light term, C. And the visibility term is equal to, basically equal to the transmittance. So it means this line, how much we are into the cloud, the visibility. So in reality, we have to also do a Raymarching here to see how long we are into the light. We are inside the cloud. So this visibility term is just equal to the shadow map times the volume shaded, and volume shaded is just the transmittance. So this is how we, and the phase but usually we just ignore this the Rayleigh the phase function, the Rayleigh scattering and the Mie scattering. It's that because when the light is coming into a median, it will scatter into different direction by different amount, and we have a phase function by an angle. But let's just ignore that. So in this implementation, actually we are going to simplify that. Let's see. Let's say if we really wanted to use the correct formula, and we have our I here, and we wanted to calculate this point, what we have to do is we have to Raymarching into it, and then for each point we also have to Raymarching to the sun, like this. And we have to calculate the transmittance, this line, this line, this line, this line, and also this line. And if we have something that is opaque and behind the cloud, we also have to integrate it and multiply by the transmittance. So this guy will be the first term here, the transmittance multiply this guy. And this integrate term is just equal to, we have multiple, so this is an ON square algorithm, Raymarching. Of course, we are not going to use this in Unity. So to simplify it, what we are doing in the calculation is, this is the I, this is the light. We are going to calculate the surface point, and then using the transmittance here as the volume shading. So our goal here is that for each of the point here, each of the vertex of the mesh, we are going to try to store this. And of course we can't store, we are trying, it's basically how occluded this point is along a direction. So what they do is like this. For each of the vertex, we store a direction to the most occluded direction, and the length of the length of the direction. So for each point, we can reconstruct roughly how occluded it is at each point. So we will store two data, the direction and the length. And we can calculate this inside Houdini. And just to read the slide, yeah, they have the vex code, but this is basically easy. We just pre-calculate the occlusion by Raymarching. We first casting out lots of rays in Houdini and then just calculate the average occluded direction and the distance. So inside Houdini, this is what we are going to store. So when we are going to shading, we are just going to reconstruct this distribution and use this to estimate the transmittance from the light source. Let's say the light source is here and our eye is here. Then we have this direction, we have this, so we can just estimate the transmittance to shade the light. So in the implementation, it is actually quite easy. This is the main code here. We store the direction into the XYZ, and the UV2Y we store the occluded length. And this is all calculated in Houdini, and we are going to back it into the vertex data. So we are also going to calculate the light in the vertex shader, not going to use it in the fragment shader. We assume that the distribution is quite uniform. And you see, we are not doing any Raymarching or loop or texture sampling. Basically, we are just calculate the transmittance and pass to the final composition post-processing shader to composite the final result. Yeah, so we just, for each of the vertex, we get the normal, and we get the view space position, its position in the view space, and we get the linear depth, and we set the output position into the projection space. And this is the key part. We decode our data inside the UV and recover them from the Houdini object space to Unity's world space. So we have the occluded direction and the occluded distance. And so we can just, using the Lambert law to calculate the transmittance by basically calculate the transmittance, the transmittance here. And just a dot product between the light direction and the occluded direction. And then we raise to a power. So we can get this lobe-like shape. And we just pass the transmittance to the final composition. It's done. So it's super cheap and fast.